Welcome to the webinar. Let's get started. Today's topic is, do bow ties have a place in alarm management? You will all be muted, just like other webinars, and if you have questions or comments, please enter them into the questions box, and we'll take a look at them at the end and probably answer them offline and send the answers to everyone. So thanks again for joining. My name is Todd Stauffer. I'm the Director of Alarm Management here at exida. Been involved with alarm management and the ISA 18 committee back before 2005. Actually helped write that standard. That was used for the creation of the international standard on alarm management, IEC 62682. I've also been involved with the ISA 18 committee to do other things, such as create technical reports, and currently as the co-chair for a new standard on process safety controls, alarms, and interlocks. Essentially things that you use for safety that do not go into an SIS, that have a risk reduction factor of 10 or less. If you're not familiar with exida, this is our 20th year of being around. We were founded with the goal of making the world, process plants that is, a safer place, with an initial focus on functional safety that branched out to cybersecurity and alarm management. If you've ever put together a safety instrumented system and designed a safety instrumented function and worked with SIL rated equipment, chances are it was exida that did that certification. We not only certify equipment, but we also certify people to help them gain and demonstrate that they have the competence necessary to execute functional safety tasks. We have a suite of software for design and engineering and essentially following the whole entire functional safety lifecycle. One part of that is called SIL Alarm, which is an alarm rationalization tool that's used with specific control systems. Actually, it works with any control system, but we have specific relationships with Rockwell and Emerson for use of the SIL Alarm tool. So what I want to start off with is some motivation about what we're talking about and why we're talking about it. And the question to ponder, to think about is, are we getting better at process safety? In the last 20 years or so, have we made things safer? Depending upon how you look at it, studies have shown that from an occupational safety point of view, there have been significant improvements. The number of lost time or recordable OSHA incidents in the US has gone down almost an order of magnitude. However, process safety incidents or major accidents have not gone down, both based on their frequency and the significance of each. And that's borne out by statistics as well as anecdotally. If you think about how often now you hear in the news about a significant major incident occurring, we can see that process safety is struggling to improve. So why is there a difference between occupational safety and process safety? Why is process safety not getting better, not improving? Some postulated that the reason is there's a lack of focus in process safety on those major hazards during operation, and that most of the emphasis is on the design stage with those hazards. Certainly a lot of effort put into PHAs and HAZOPs and such, but the use of that information once you get into operation, not quite so much. And that is postulated as the major reason why process safety has not improved. I would say, or I would propose, that the major cause of process safety incident nowadays is not really technology related. We know enough to design systems with reliability built in and redundancy. Now we have more of an issue with the processes and the people, whether it's ensuring that the people have the appropriate level of competence, that they're using procedures appropriately, that human factors are taken into account appropriately, that management and supervision is occurring correctly and appropriately, and that the right level of safety culture is in place. If we look at these levels of reliability, we've gotten pretty good with the engineering reliability. It's the softer ones that relate to human factors and organizational factors where the problems occur. So it's been recommended that a way to improve process safety is to focus on the use of barriers for risk management. And one of the best ways to visualize barriers and understand how they're used and what they're used for is through a bow tie diagram. So this webinar is going to combine those two topics, the use of barriers for risk management and bow ties for risk management and communication of risks. So we will look at what barriers are, what the bow tie methodology is about, where it came from. We'll dive into what the structure of a bow tie diagram looks like, where it's being used, and we'll look at some detailed examples of incidents, where bow tie diagrams are used to define the accident scenarios and the causes and the preventive barriers that failed and ultimately resulted in that incident. We'll also take a look at what some of the key benefits are of using bow ties. Now, the majority of the material for this presentation comes from a relatively new book from the CCPS AICHE called Bow Ties in Risk Management. It's called a concept book because the purpose of it is to promulgate knowledge about this new technology or new approach. And I say it's new, although it's not really. It's been around for 20 years plus. But in terms of having a standard for how it's applied or used, one doesn't quite exist yet. So this is a step to go down the path of increasing adoption and understanding of bow ties and how they're used. So we're going to consider this a concept webinar as well on how to use bow ties and barriers in alarm management. So a definition of a barrier: it's a risk control element that seeks to prevent unintended events from occurring or prevent escalation of those events into significant consequences. There are preventative barriers as well as mitigative barriers, and there are barriers that are made totally from hardware only. There are some that are passively designed. There are some that are made up of just human behaviors and human responses. And then there are some that are a combination of human plus active hardware barriers. Now, one of the ideas for the use of barriers comes from the Swiss cheese model that is promulgated by James Reason. And he proposed that in typical industry accidents, it's not caused by just one failure, that there are typically multiple things that fail at the same time. And we could think of them as slices of Swiss cheese. And those slices of Swiss cheese act to prevent hazards from escalating into an accident. But no barrier or no slice is 100% effective, and that's what the holes in the Swiss cheese represent. Those are from degradation factors, which we'll talk about later. But the idea is, if those holes in the Swiss cheese layers line up, then a hazard can make its way through all of the preventive barriers and result in the top event or the accident. So the idea of barriers was really brought into the forefront, the use of barriers through this Swiss cheese model. Bow ties build upon this and create a similar structure that's better able to visualize all of the elements that go with the barriers and to be able to show more complicated scenarios where you have multi-threat legs of consequences and potential causes. So what is the bow tie methodology? It's really a tool for communicating how the control of major accident events is achieved. It's meant to be a clear, easy to understand way to grasp the risk assessment results and understand how the risk management process works and an individual's role in that. It's designed and targeted to be easily understood by plant personnel at various levels. So down to the operations people, maintenance, management. It's designed to not be too overly technical, but to be able to communicate in a very simplistic, easy to understand way the key risk factors and the key barriers that help prevent those risk factors from promulgating. Now, it supports design of safety systems and such, but where it really comes in handy or really shows its excellence and its usability is in its focus on operational aspects related to safety. So it does a great job at highlighting what are the most important barriers to prevent a hazardous event from occurring. It helps to be able to understand and how to monitor and assess the effectiveness of individual barriers and whether they're operating adequately. And it helps to focus on the degradation controls that help maintain those barriers and make sure they stay effective. So bow tie methodology supports both barrier management and the addressing of human and organizational factors, which, as I said earlier, I believe are the key things that are driving process safety incidents nowadays. From a technical point of view, a bow tie diagram illustrates the causes or most likely potential causes that could escalate or evolve into a critical loss event, including the barriers that it must progress through to get there. And then it also shows from that critical event how it might escalate further to end up with an incident or an accident, or essentially a main accident event. The left-hand side of the bow tie diagram, the preventive side, can be thought of as a fault tree that shows how the causes contribute and lead to that critical event. And the right side is an event tree that shows how the mitigative measures either prevent the consequence or reduce the impact of that loss event. In terms of where the bow tie methodology came from, it's attributed to ICI, empirical chemicals, and it's related that it was first talked about in 1979 or the early 80s in a training class that was taught at the University of Queensland in Australia. Shell is credited as the first company that really adopted the use of bow ties in a major way in the 1990s, making it into a global business practice for managing risk. There's also been some research projects such as the Aramis project in the EU that dove into how to use bow ties as a framework to comply with the Seveso II directive. In terms of adoption, it's used around the world. It's been in use for the last 20 to 30 years, particularly in Asia Pacific, Australia, New Zealand, in Europe, Norway, the UK. It's also used in aviation and railways, not so much in the US yet, although the API is starting to create regulations and guidelines that relate to a barrier management approach. Certainly the UK and the HSE has been a leader in the use of barriers and bow ties as a tool to model barriers. And Norway as well has focused on barrier management for the offshore industry as a key tool to manage risk. So when are bow ties used? Well, they could be used to address all different types of scenarios, but the primary time they're used is related to the control of major accident events. These are the large-scale events that have major significant consequences. Hopefully you have a concept of what that means. The definition is a hazardous event that results in one or more fatalities or severe injuries, potentially extensive damage to infrastructure at a plant, or persistent or significant impact to the environment. So the worst case consequence scenarios in your plant can likely be identified as major accident events, or MAEs. So the bow tie structure then is what's in place to hopefully control those MAEs. So if we look at this diagram, and again, this is taken from the CCPS concept book, the elements on the left side are the preventive side. We have barriers and threats to potentially lead to the top event. The right side is the mitigation side, with these consequences over here lining up with what we just talked about, the major accident events. So we're going to talk about each of these elements in quite some detail very shortly. This is a summary slide that brings together what all of those elements are and how they're defined. If we think about what information is shown here and where it might come from, we have a potential hazard, we have threats or likely causes, we have barriers or safeguards. So a lot of the information that we see on here is very similar to that which would be documented in a HAZOP or a hazard. And that is an important point. There's a significant difference between bow ties and HAZOPs. HAZOPs, one of the main purposes is to identify previously unknown hazardous situations. So it's really excellent at identifying the hazards. The bow tie structure, bow tie diagram, is not so much for identifying, it's more for communicating those hazards as well as the barriers that are in place to prevent the hazards from escalating to a top event or to an incident. So they have different purposes. A bow tie would very likely display information coming from a HAZOP. As we mentioned, the bow tie on the left-hand side is the fault tree, and on the right side is the event tree. Now let's dive into the elements in that bow tie diagram. The first element we'll talk about is the hazard. That's the operation, activity, or material with the potential to cause harm. And the idea is this is something that is present as a part of your business. It's part of the day-to-day doing business. So an example here is the gasoline stored in a tank. Well, if you're a refinery, that's part of doing your day-to-day business. So most likely in a HAZOP or a hazard, that was identified as a potential hazard. The top event then is the moment when control over that hazard is lost and it starts to release its harmful potential. So most common top events, the most common top event is a loss of containment event, but other commonly used ones would be a loss of separation or a loss of control. So in this example, the top event is a tank overflow, or more specifically, tank overflow and gasoline spill onto the dike floor. Now let's move to the right side of the diagram and the consequences. So they are the unwanted outcomes that could result if the top event is allowed to propagate and lead to the damage or harm. So this is essentially the major accident event scenario. What is that worst case thing that could happen? Now, one top event most likely would lead to multiple different consequence scenarios. For the purposes of the bow tie diagram, we don't necessarily need to show every single potential combination. In fact, it's more important to show the most important ones that we want to focus attention on. So the completeness of the bow tie from a documenting every single scenario is not necessarily the purpose. It's more to raise visibility to the major hazards and the major consequences and the major barriers that are used to prevent those. So in this example, we're showing the consequence as fatalities due to a fire. Threats then are on the left-hand side of the of the bow tie diagram on the preventive side. So the threats are the potential reasons or causes for the loss of control of the hazard that leads to that top event. And typically you'll have multiple potential threats that can lead to that top event. Now, part of the benefit or part of the reason of this book coming out is because it defines some of the best practices and the rules that have been put in place by those that have been working with bow ties for years and years and years. And one of them has to do with how you define a threat. A threat or a cause here needs to be pretty significant. It has to have direct causation, meaning that it is specific enough that if it occurred, and it also is sufficient that if it occurred and there was no preventive barrier, that it would result in that top event. So there needs to be that significant direct causation relationship for something to be considered a threat or a likely cause. There's 3 different categories. Primary equipment not performing within operating limits is one. External influence, environmental influence is another one, and operational issues is the third most common category for threats. So in this case, the example that we're showing, planned fill volume of the tank exceeds the residual capacity. Now, one of the mistakes that is sometimes made is putting human error down as a threat. Doesn't really belong at this part of the bow tie diagram. Human error is not specific or sufficient to lead to a tank or to lead to the consequence in most cases. We will see that human error does come into play when we look at the degradation factors and things like that that could cause the barriers to not work effectively. So let's look more at barriers. And a barrier we talked about earlier, definition of what it was, physical or non-physical measures to prevent or mitigate unwanted events. Here we see a couple of different types of barriers. There's some that are behavioral or all human, and the terminology of what types of barriers there are is different depending upon what source you look at. Socio-technical is another one, sometimes called human, as we'll see later, but you can see it's a combination of technology and human together. We have active hardware, like a safety instrumented system, continuous hardware, like a ventilation system, and then we have passive hardware, like a dike or a bund. You could think of them all as having different levels of reliability. Now, one of the, again, rules or characteristics that's been defined for a behavioral or socio-technical or active hardware barrier, so active or human, it needs to contain 3 elements. It needs to have a detection element, a decision element, and an acting element. Very similar to a safety instrumented function. So it has to have some part of it that does the detection of the abnormal situation, some part of it that makes the decision that something has occurred and what action needs to be taken. So in a safety instrumented function, that would be our logic solver. And then it needs to act or perform an action. Final element, in this case, closing an inlet valve. If it doesn't contain all 3 of those elements, then it's not considered really a barrier. So if we think about an emergency shutdown valve or system, that by itself, or the valve, is not a barrier because the valve is just taking the action, it's doing the action. So to become an effective barrier, to be considered a barrier, it needs to have a detection and a decision element. So a sensor to detect that something has gone wrong and to take the automatic action of closing the shutdown valve, or a sensor to generate an alarm and notify an operator who then presses a button to initiate that emergency shutdown. So it needs to contain all 3 of those elements to be considered a barrier in a bow tie diagram. Additional to ensuring that you're using the right things as a barrier is they also really need to meet the same requirements or characteristics that you would find in an independent protection layer. So in a LOPA analysis or whatever. So they need to be independent, generally speaking, auditable and dependable. So again, defining the characteristics or requirements of what qualifies as a barrier. This is a more detailed list of the different types of barriers defined in the CCPS book, and you can see it uses some different terminology, particularly in the human barrier area. And one of the more interesting ones, and the one that we'll spend a lot of time talking about today, is this active hardware and human barrier, which is essentially a combination of human and technology together. And again, it needs to include a detect, decide, and act element. So the detection is fulfilled in this example by a sensor and a high level alarm. The decision is the operator hearing or seeing the alarm and determining what needs to be done. And then the action would be them executing or something through the HMI, or walking out into the plant and opening a valve or something manually. It also could be the evacuation in the event that a toxic gas detection leak is noticed. And this illustrates the barrier element, or why this is so important. So toxic gas detector just by itself and generating an alarm is not a barrier unless the operator knows that the action that they take is to evacuate the area. So there are two different types of barriers, depending upon whether it's on the left side or the right side of the diagram. If it's on the left side, those are prevention barriers. So they prevent the threats or the potential causes from escalating to generate the top event. They do that by either preventing the threat from occurring in the first place or stopping a threat from proceeding to the top event. Now to be a valid barrier, they need to be able to prevent that threat on their own from making it to the top event. So they need to be significant enough to essentially stop it in its tracks. Mitigation barriers are on the right side of the diagram. They need to be able to act after the top event has occurred to prevent the consequence from occurring or to mitigate the significance of it. Looking at a typical scenario that we often talk about in alarm management and safety together, we have layers of protection, the generic layers of protection to prevent, excuse me, a abnormal situation from escalating into an incident. We have a layer of protection that relates to the process design. The example here would be the steel containment envelope as a barrier. We have layers of protection for the process control system and the operator response to an alarm. That might be another barrier. Then we have a SIS trip. And then after that, higher up in the hierarchy, we have the relief system or a pressure relief valve. So the layout of the barriers is important in terms of their order. It should be laid out in the appropriate time order or the order that the demands actually would occur. So consistent with this diagram, the operator response to alarms is one of the first barriers that would be hit. And if they're not effective, that's when the SIS trip barrier would come into play or the relief system barrier. So now let's look at the last couple elements of the bow tie diagram, the degradation factors and degradation controls. So here's a different example where we're concerned about loss of containment of propane and that leading to a fire or explosion. So the preventive barrier that we have, the mitigative barrier is an emergency shutdown with a manual actuation following gas detection. So that is the barrier. The degradation factor is, what if that emergency shutdown system failed to isolate the leak? How could we deal with that? What actions or controls could we put in place to counteract the potential of the degradation factor or to make it so it doesn't compromise the barrier? So here's 3 examples of degradation controls: the gas detection system regular maintenance, testing of the emergency shutdown valve. So things that would prove out that the ESD system is going to work correctly when it's called upon. So that's our combination of degradation factors and degradation controls. Now, what we've been looking at so far is a standard bow tie diagram. There's also something called a multi-level bow tie diagram, or with extension levels, that essentially moves the position of the elements on the bow tie, allowing you to focus on something different. So for example, if we wanted to focus on one of the prevention barriers, the level 1 extension takes that barrier and makes that into the top event. So then we look at things differently in relation to that. So something that was a degradation factor previously now becomes a threat, and something that was a degradation control now becomes a barrier. This allows us to create more detail in the degradation control and degradation barriers. degradation factors and degradation controls, and go into much more detail there. And that's really where the human and organizational factors elements that are necessary to be put in place to control the barriers or to manage the barriers, that's where some of that information in detail really comes out. So let's apply that to a commonly known incident that occurred at the Buncefield depot in 2005, I believe, 2009. So we're dealing with large tanks that have a level gauge for measuring the level that will generate alarms. They also have a independent, separate high level switch that will automatically shut off flow and generate alarms. And we can see that there's supposed to be a empty space up here below, above the max fill level of the tank. So what happened in this incident? Well, the tank was being filled by crude coming in from the North Sea, and the operator was essentially waiting for the level gauge to indicate that the tank was full by generating an alarm. He was waiting for the high level alarm to occur that would tell him it was time to shut off the incoming flow. That tank level gauge failed at about 2/3 full and did not generate any diagnostic alarm to indicate that it failed. And then once the level in the tank was full, it didn't generate the alarm to tell the operator it was time to turn off the flow. So that alarm failed to enunciate. But the high level automatic safety switch should have kicked in after that to notify the operator that the tank was full and to automatically shut off the incoming valves. Well, unfortunately, that didn't work when it was supposed to. So that led to the overfilling of the tank, the release of hydrocarbons, big fire, big explosion, and billions of dollars worth of damage. Luckily, no one was hurt or killed, but there was significant damage. One of the other attributed causes was poor design of the human-machine interface for the operator. So now let's take a look at the Bowtie diagram for that incident. And if we look at the prevention side first, the threat is filling the tank more than what it can handle, which we know was what ultimately happened. The hazard is the gasoline in the tank, and the top event is the tank overflow. We have 3 different barriers defined. First one is procedurally that there's a plan and proactive monitoring for filling the tank. Second is the tank high-level alarm and the operator response to it. And third is the independent high automatic shutoff with alarm. So 3 barriers to potentially prevent that from occurring. If we look at the mitigation side, once the tank starts to overflow, that didn't necessarily mean that we were going to have the explosion. There were mitigation barriers in place that were meant to prevent the incident from escalating to where it ultimately ended up. Now, some of these mitigation barriers failed, like the bund and the dike, essentially not able to perform the role that they were designed to because of the fires that were occurring. So this is the mitigation side. We can see that there weren't fatalities that occurred, which was actually pretty lucky. And one of the maybe perhaps barriers that prevented multiple fatalities from occurring was the day of the week that the accident occurred. It was on a weekend. So luckily there were not a lot of people at the plant and not a lot of people in the area around the plant, or else this would have been part of the accident description as well. So let's go back to the prevention side and focus on the second barrier, the tank high level alarm and the operator response. So if we dive into more details, we can see that there would be two degradation factors defined. One is that the alarm fails to enunciate, essentially, which is what happened. The way that that would be addressed, the degradation controls for that would be regular maintenance and testing, and making sure that if there was a failure, that it was easy to see in the control room and that that would be fixed quickly. And if we look at the other degradation factor defined, it was the operator failing to respond appropriately to the alarms, with 4 different controls in place to prevent that degradation factor. Alarms being easily identified within the HMI, having predefined operator actions for what they should do if that high level alarm occurs, ensuring that the operator is fit for work in terms of fatigue, sleep, etc., and supervisory enforcement of importance and situation awareness. We're not going to focus so much on those last two, but the first two we're going to look at in more detail here. So if we create the level 1 extension and make the top event now that barrier failure, the high level alarm, then that allows us to dive into more detail of this threat now, which was a degradation factor before. So if we look at what could be in place to prevent the operator from failing to respond appropriately, it would be making the alarms easy to identify in the HMI, which could be compromised by alarm overload, which would be addressed potentially by alarm rationalization and prioritization. Another degradation factor is the alarms being hidden behind other windows within the HMI. So degradation control there would be ensuring that the HMI is designed appropriately to be able to see those alarms. Looking at the other side, the definition of the operator action, ensuring that the operator is able to take that action, and there's no reason why they wouldn't, such as if they were going to be stopping production, there might be an unwritten rule that thou shalt not do that. So the operator needs to have the authority and the responsibility and the understanding that they have the power to take the corrective action that's needed, even if it results in stopping production. The other defined degradation factor here is that the operator action that may have been defined did not consider all scenarios. So the way to deal with that is to go through a structured alarm objective and response analysis. So stepping back and looking at all this, what we see is some degradation controls and factors that could be specific to this case, but most of these are actually generic and could be used in other bow tie related to this site, or in general, these would be good alarm management practices to follow. So looking at that in more detail even, we looked at the first 2 barriers. We're not going to dive into these other 2, but you can imagine if we were to show all that, this becomes a pretty detailed diagram. If you do the full build out of that threat pathway, something that's really getting kind of complicated to use and probably not good for the general communication of risk management. In this case, it dives into the specific realm of providing information to the process safety engineer, the controls engineer, etc., with the extra level of detail of specificity here. So from an alarm management point of view, what do we take away related to the barriers and the degradation factors and controls? Well, to prevent or to deal with the alarm annunciation failure, we need regular maintenance and testing and ensuring that that's readily noticeable within the HMI. To help address the operator failing to respond to the alarm correctly, we need to make sure that the alarm is easily identified in the HMI. They're not overloaded with alarms, or there's not windows preventing them from seeing the alarm. We also need to make sure that the defined operator action is understood, what they need to do in the event of that alarm. So from an alarm management point of view, if we think about the alarm management controls to counteract those degradation factors, one of the generic things that should be done is to create an alarm philosophy document. In the philosophy, we define alarm classes or classification, and we could set up a classification that allows us to identify alarms that are used as safety barriers. Hopefully there's only a handful of them, so being able to identify them like that would allow them to get the extra attention that they need during rationalization, as well as to define for them that they need a different maintenance protocol in terms of testing and calibration and such to make sure it's going to work. They also might call for additional detail and thought in the alarm philosophy about how to deal with diagnostic alarms coming from those sensors. In addition to the alarm philosophy, then, we would also perform alarm rationalization, including prioritization and an alarm objective analysis, a structured alarm objective and response analysis, which would really be a part of rationalization as well. In terms of what we would do with this information and accomplish with it, we would use that to provide training to the operators on these specific alarms. So the alarms that are used as barriers, you better believe the operator needs to be trained on them and probably drilled to make sure that they know that response. They're very familiar with it. There should also be alarm response procedures created for those alarms from the results of rationalization. And we need to make sure that, again, those actions, the procedure is actionable by the operator. So there's no hesitance for them to take that necessary action, either from the shutdown of production or ensuring that it doesn't put them in an unsafe situation having to take that corrective action. Now let's continue and look at the Buncefield situation and results in a little bit different way. So this is information from a presentation that was done at a ICHEM-E conference in 2018. Here, again, for the Buncefield tank overflow incident, we've done a more complete documentation of all of the potential threats that might lead to that loss of containment. And we can see that the high level alarm as a barrier shows up 4 times in terms of helping to prevent those threats. So if we reorient the Bowtie diagram to have the level alarm as in the position of the top event, that allows us to focus much more on the alarms and the impact of alarms and what they do. So here we can see for this particular high level alarm, what are the potential causes or threats that could lead to it? And then what are the consequences that might occur if the alarm is not responded to in time? Now that's the information that's discussed during alarm rationalization. So alarm rationalization would be a great source of this information, or if rationalization has not been performed yet, this diagram would be very useful as a starting point to drive that rationalization. This information could also be used then in the creation of alarm response procedures. We have the likely causes here on the left, the potential consequences here on the right, and we would need to define the corrective actions. Now, some people also believe that there's a dynamic element to this, and one could take this and use it to guide and help the operator determine what to do or determine what has happened by kind of indicating which is the cause that led to the alarm, which would drive them to hopefully take the appropriate corrective action, which may be different depending upon which cause was the initial trigger. So now switching gears and talking about another incident that occurred and how bow tie diagrams were used to talk about it. This is one that occurred in the US and was investigated by the Chemical Safety Board. Incident occurred in 2018. There was a well blowout and a rig fire that occurred, leading to the death of 5 workers. So the Chemical Safety Board investigated, and in their report, they spoke about the incident from a barrier and bow tie point of view. And they actually included an example of what the bow tie diagram looked like, which we'll see in a second. So this is the first instance that I know of, it may not be the first, where the Chemical Safety Board was communicating the risk information in a bow tie format. So here they said, when they summarized what happened, it was basically the failure of 2 barriers. Failure of a primary barrier on the preventive side, which was hydrostatic pressure produced by the drilling mud, and then failure of a secondary barrier, actually on the mitigation side, which was human detection of an influx of gas and activation of the blowout preventer. Idea being an alarm should have been generated to tell the operator that it's not doing what it's supposed to, and the corrective action would have been activating the blowout preventer. So both of those barriers failed. When they defined the contributions to those causes, you can see, again, barrier terminology and discussion was used to talk about that. Insufficient degradation controls in place to maintain those barriers. If we look at the verbiage of these other contributory causes, we see things like operations proceeded without needed planning or procedure. Driller had difficulties with an electronic worksheet. It was an incorrect determination of pressure. There was a lack of detail in procedures. The alarm system was actually turned off. Deficient policies. Drillers were not tested to understand to provide or demonstrate competence in in being able to detect the influx to know that they needed to take a corrective action. Where flow checks were not conducted appropriately. They didn't effectively monitor the implementation of policy. So what do these sound like? They don't sound so much like a failure of technology to me as, again, a failure of human and organizational factors, procedures, competence. All of these went into the failure and led to the failure of those 2 barriers. So here we can see the barrier diagram, the bow tie. Apologize, it's a little bit hard to see or understand. On the right-hand side is the mitigation barrier, which is where the alarms show up. In addition to what we just saw, the Chemical Safety Board report also identified a couple of alarm management specific recommendations. One being that an alarm philosophy should be developed or should have been developed. Alarm rationalization should be performed. The drilling industry needs an alarm management standard, and state-based alarming capabilities should be provided. So significant takeaways from the accident investigation from an alarm management point of view, from an application of bow ties and barriers, and documentation that you need to create an alarm philosophy and you need to perform alarm rationalization. So if you don't know what those things are, or you've not done those in your plant, it's time to start thinking about them, because that's something that Chemical Safety Board and auditors and insurance regulators are going to start to be looking at more and more as it becomes more prevalently discussed in the context of these incidents and accidents. So one of the other things that bow tie diagrams do really well is help identify safety critical tasks and safety critical elements. And if you're already familiar with bow ties, you might use different terminology there, but this is what's defined in the CCPS book. So a safety critical task is a task where the human or organizational factors either could cause or contribute to the accident, or where their purpose is to prevent the accident or limit it from it occurring. So, and safety critical tasks would typically be a part of barriers. Safety critical elements or equipment is parts of the installation, plant, equipment, logic that would, again, either cause or contribute to the accident occurring in the first place, or be used to prevent or mitigate the accident from occurring. And these would also be typically parts of barriers. So now let's look at the bow tie analysis again for Buncefield and think about, of these barriers, which ones are safety critical tasks and which ones are safety critical elements, and what does that mean? So if we look at the first barrier that's in place, which was to have a procedure for the plan for filling the tank and proactive monitoring, I think we could define that safely as a safety critical task. That needs to be done successfully, or else that barrier potentially is going to be compromised. So in terms of raising visibility to the importance of that, that's what identification as a safety critical task can do. Once that is done now, that means we have increased, or the potential for increased, responsibility and accountability for that task being done correctly. So the work procedure might be more formally documented in procedures. There could be work instructions. There could be performance standards to validate the execution of that process. There could be verbiage put into the job description of an operator to ensure that they know how to do that. There could be training to make sure that they are able to execute that safety critical task correctly. And there might be competence requirements defined to ensure that the operators are able to successfully execute that. Certainly the tank level alarm, the high level alarm, and that sensor would probably be considered a safety critical element, with maintenance required to keep it running as a safety critical task. So again, what's the benefit of identifying this as a safety critical task? Well, now if I'm part of the maintenance team for this plant, the highlighting this as a safety critical task helps me understand the importance when I do maintenance for this particular device. And it also helps me see how my job impacts the risk management of the plant. So you can see how your individual role impacts the risk assessment and the risk mitigation to prevent incidents and accidents from occurring. So it's a great way to raise visibility so that appropriate procedures and management structure and systems can be put in place to make sure these tasks get executed correctly. Barriers can also be used to define process safety leading and lagging indicators, depending upon what they are. So safety critical alarms, for example, and how often they activate correctly. So this helps then in the performance monitoring of the effectiveness of the barrier. It would also help for auditing to make sure the barrier is being maintained the way it's supposed to. These indicators could come from specific barriers for certain scenarios, or perhaps from the more generic barriers that show up in multiple bow tie diagrams. So that's drawing to the end of the presentation. So let's look at some of the main points that we covered. So bow tie diagrams are very useful for communicating how safety barriers, protection layers, prevent or mitigate major accident events. They excel at helping to focus on the operational aspects of safety and human organizational factors, which I believe is the primary cause of process safety incidents today. They help identify safety critical tasks and safety critical equipment for escalation of accountability and responsibility. They help address the degradation factors that cause barriers to fail, so people know who is responsible for that and how frequently they need to execute the tasks that are required there. It identifies who is responsible for the management of a barrier and how an individual's day-to-day role impacts the risk of the plant, and how some of the things that they do actually are critical to minimizing the risk. Highlights the importance of alarm management from a generic point of view. We also talked about alarms being used as effective barriers, and we saw some specific degradation factors, things like operator being trained on how to respond to that particular high level alarm that's used as a barrier. We also saw some generic degradation factors and controls, like performing alarm rationalization to ensure operators aren't overloaded by alarms. And in general, I would say that to address the alarm-related degradation factors in the bow tie diagram, we would want to follow the alarm management life cycle as defined in the ISA 18.2 and IEC 62682 standards. So on that note, I'll say thank you for attending. The last thing I want to share is a little bit about the upcoming training that exida has. We have a suite of different offerings for online live training, as well as online on-demand pre-recorded training. So if you're like me and probably many other people around the world and working from home and trying to make that as productive as possible, one of the great things that you can do is learn new skills, and taking some of these training classes would be a great way to possibly do that. So I encourage you to check them out. There's a alarm management class scheduled for next week or 2 weeks from now, and then another one occurring in the beginning of June, sorry. And as I mentioned, those same courses, or many of those same courses, are available in a self-paced mode so that you could look at them per your schedule from 1 o'clock to 3 o'clock in the morning every day. However you like to work, you can interact with the training material and make sure you get out of it what you need. So I encourage you to check them out. In terms of the references that were used for the creation of this presentation, they are listed here. And as I said earlier, the main reference that was used was this book, Bow Ties and Risk Management, from the CCPS, a relatively new book. So we'll just take a quick look to see whether there's any questions. I don't see any right now, so we'll take a look at them after the fact and then get back to folks. So if you have any questions, feel free to shoot me an email. I'd be interested in understanding about your thoughts on bow ties and alarm management as part of bow ties. If you enjoyed this webinar, I'd encourage you to check out the other upcoming webinars, as well as those that have been recorded in the past, have been run in the past. They're available for viewing through Exida's YouTube channel, which you can get access to from the Exida website. You'll see quite a variety of topics and webinars available in alarm management, functional safety, cybersecurity, etc. So on that note, I'll say again, thank you very much for attending. I hope you found this to be an enjoyable and useful webinar, and I encourage you to attend others in the future and have a good rest of the day.